Hello students, today let us see the verification of 4-bit DAC using an op-amp. The aim of this experiment is to design a 4-bit R-2R digital to analog converter for required step size. Okay, the components required are a regulated power supply to supply VCC and VEE to the op-amp, a trainer board or a breadboard, and resistors R and 2R. So the R and 2R, as we cannot achieve exactly the double value of R in terms of generalized resistors, R2R can be achieved in two ways. One is to select any resistor value for R and connect two 2R resistors in parallel to get an R. Okay, the other way around is select a resistor R and connect two resistors of R in series to get a 2R. Either way we can achieve R and 2R exactly. And we need an operational amplifier to amplify the signal. Okay, here we are going to use an LM741 op-amp. So this is the circuit diagram of a 4-bit R2R ladder network DAC, in which the LSB is at the left hand side and MSB is at the right hand side. Okay, we need only two resistors R and 2R to construct a DAC of any bit length. Okay, here we are using R for RF. Okay, R for RF, which gives the gain 1. Okay, you can choose any value of R to get required step size. Okay, next, coming to circuit analysis. Here this is the circuit as we discussed earlier. Okay, to analyze the circuit we need two theorems. One is a Thevenin's theorem and another one is a superposition theorem. A Thevenin's theorem states that any linear circuit containing several voltages and resistance can be replaced by just one single voltage in series with a single resistance connected across the load. So this is what a Thevenin theorem states, and a superposition states that for a linear system the response of voltage or current in any branch of a linear circuit having more than one independent source, that should not be a dependent source, independent source, equal to the algebraic sum of responses caused by each independent source. So this is how a superposition theorem states. Using these two theorems we will analyze the circuit. Okay, so to understand, let us understand the analysis. Let us assume only one bit is high or one bit is applied with V reference. Here it is a 5 volts at a time. Case 1, the input sequence is 0 0 0 1, that is LSB bit is applied with V reference, which is 5 volts, and remaining bits are connected to ground terminal. Okay, from this terminal, these toggle switches can be toggled to either V reference or to ground to apply respective binary inputs. Okay, next, so coming to the analysis part. Now as we know, we are going to apply 1 to the LSB bit, hence the LSB bit is applied with V reference of 5 volts and remaining bits are connected to ground. So now we can see there are two 2R resistors connected in parallel, the highlighted portion. So here we can apply Thevenin's theorem. So using Thevenin's theorem, we will simplify this circuit to a single voltage source VTH and a single resistance RTH. So let us by using the Thevenin's theorem, the VTH equal to applied voltage V reference into opposite resistance by total resistance. The applied resistance is applied voltage is V reference multiplied by resistances are equal resistance of 2R. So there is R by R plus 2R plus 2R. So that is V reference by 2. So that is VTH, and RTH is the parallel combination of two resistors. So the resultant will be the resultant of a two parallel resistors of equal magnitude will be 1/2 of the resistance value. Like, or else you can simply calculate using Ohm's law. So RTH equal to R. So the simplified circuit can be represented with R and VTH, RTH and VTH. So in the next diagram, it is shown that the two R's in parallel is replaced with a R, and the voltage source V reference is replaced with V Thevenin's equivalent voltage V reference by 2. Now if you observe the highlighted portion, it shows that two R's are connected in series. So from Ohm's law, the total resistance will be 2R, isn't it? Next, coming to the next portion. Here what happens? The two R's are connected, okay, with V reference. The same circuit is represented here. So the two resistors are made into one 2R, okay, with applied V reference by 2. Now once again, if you see the highlighted portion, same circuit will appear with different reference voltage. Now the reference voltage is VTH, which is V reference by 2. Again using the same formula, we can reduce the circuit to using Thevenin's theorem. VTH here is applied voltage is V reference by 2, and two resistors are equal magnitude 2R and 2R. So the VTH equal to applied voltage into opposite resistance by total resistance. So that yields to V reference by 4. Now this is our VTH. So this VTH is applied to the resultant RTH. Okay, isn't it? RTH is again parallel combination of two resistors of a magnitude 2R. So the resultant RTH is R. Okay. So now again the circuit is reduced to R and R with V reference by 4. This parallel combination is reduced to RTH and VTH. Okay. So again that is connected to a series resistance of value R. So again using Ohm's law, this will be 2R. So 2R is applied with V reference by 2, and that is connected to a parallel resistor of 2R. Again the circuit will become this one, R-2R parallel combination followed by applied with a V reference by 4. So this circuit will be modified into this portion. Okay. Now again by applying V Thevenin's, what will be the Thevenin's equivalent voltage? V reference by 8, and equivalent resistance, Thevenin's resistance equal to R. So using Thevenin's theorem, VT equals to applied voltage V reference by 4 into opposite resistance by total resistance, which is V reference by 8. Resultant VTH is V reference by 8, and RTH is a parallel combination of two R resistors, which is R into R, 2R into 2R by 2R plus 2R, which is equivalent to R. Okay, again same thing will repeat. So this circuit is again represented with V reference by 8 and RTH equal to R. Okay. So again these two series combination will become R, 2R, isn't it? So this 2R is parallel with another 2R which is connected to ground. Again by applying Thevenin's equivalence, we will reduce this one to a single voltage source and a resistance. Okay, using Thevenin's theorem, VTH is V reference by 8 is the applied voltage here, and the resistors are two R's connected in parallel, Hence the VTH is V reference by 8 into opposite resistance by total resistance. So that is V reference by 16. That is the VTH obtained from this circuit, and RTH is, as usual, it is R. So now the whole circuit is reduced to a single RTH and VTH, okay, with a feedback resistance of R, RF equal to R here. You can choose any value as discussed earlier. And finally, the circuit is reduced to an inverting amplifier because the input is connected to a pin number 2 with Rin or input resistance Rin equal to R, and applied voltage to the input is V reference by 16. This is the VTH obtained earlier, and RF equal to R. This is the final circuit, final reduced circuit. So hence the output is the minus V reference by 16 into R by R. R by R is the RF by R, because RF and R are equal resistors. So hence this will become minus V reference by 16. This minus sign is because the circuit is in inverting mode. Okay. Hence the output will be negative of the applied voltage, inverted input voltage. Okay. Now let us see the case 2. In this, we are applying a binary sequence of 0, 0, 1, 0. That is, bit right side to the LSB is applied to with V reference, and remaining bits as usual are connected to ground. So let us see this circuit. This V reference, this is the V reference connected, and remaining are connected to ground. Okay, this is ground, connected to ground. Okay. Now let us see what happens. So now the highlighted portion shows that two resistors are connected in parallel without any voltage source, and hence we can directly simplify it as R. Okay, isn't it? R. So now the circuit is reduced to two resistors of R and R connected to ground, and next to that one is a V reference connected to 2R. Now again, as earlier, let us simplify this using Thevenin's theorem. Using Thevenin's theorem, here the reference voltage is V reference, applied voltage to the resistive network is V reference, and the voltages are and the current resistors are 2R and 2R. So hence the V Thevenin is equal to applied voltage V reference into opposite resistance by total resistance, that is V reference by 2. Okay, the RTH is the parallel combination of two 2R resistors, which is R. Now the modified circuit will be with VTH and RTH, which is equal to R. So that is represented here. Again you can see here the applied circuit will be V reference by 2, and there are two resistors R and R are in series. Hence the total resistance will be again 2R. Now we can see a V reference by 2 is connected to a 2R resistors, which is in turn connected to a 2R resistors in parallel combination, but the 2R resistor is connected to ground. So now again let us simplify this one. Okay, let us simplify this one further. So using Thevenin's theorem, again the output the voltage at this node, the voltage the circuit can be modified into VTH equal to V reference by 2, because the applied the voltage derived from the earlier circuit is V reference by 2, and opposite resistance by total resistance is 4, hence V reference by 4. And the RTH is the parallel combination of these two resistors. By replacing this V reference with ground, we will get 2 R in parallel, hence the RTH will be parallel combination of two 2R resistors, which is equivalent to R. So this is what we will get. R with V reference by 4. The circuit is replaced with Thevenin's equivalent voltage and Thevenin's equivalent resistor R, RTH and VTH. So again, same thing will happen. What happens? This circuit is again, two resistors are in series, which is in turn will make a 2R resistor parallel with another 2R resistor which is connected to ground. Hence, again by using Thevenin's theorem, we can reduce this circuit. Okay, using Thevenin's theorem, VTH equal to V reference by 4, the applied voltage, into opposite resistance by total resistance, which is equal to V reference by 8. And RTH is a parallel combination of two 2R resistors, which gives you R. So, again finally the circuit will be modified into V reference by 8 as a input voltage and input resistance is R, and these two is connected to a inverting amplifier with feedback resistor RF equal to R. And so what will be the output? Output equal to V reference by 8 minus V reference by 8 into RF by R. Okay, which is nothing but minus V reference by 8. Minus V reference because it is connected to inverting terminal, inverting op amp, inverting amplifier. Okay. In similar lines, we can reduce the circuit with a single to a single RTH and VTH for a single source. So, hence for a 4-bit R-2R DAC with RF equal to R, for input bit sequence 0001, which contributes a V reference by 16 to output. Likewise, a 001 combination will contribute minus V reference by 8 when RTH, when R reference equal to R. If you change RF, obviously that factor will be multiplied with the VRF by 8. Okay, that thing is multiplied. Okay, for bit sequence 0100, it contributes minus VRF by 4, and likewise for 100, it contributes minus VRF by 2. So, by using superposition theorem, we can finally find out for any bit sequence. So, if the bit sequence is 1001, the output will be for 1 for 100 we will get minus VRF by 2, plus for 001 we will get V reference by 16. Hence, for 1001 we will get minus V reference by 2 plus minus V reference by 16, sum of individual effects. Final output will be the sum of individual effects, right? We can choose RF suitably to increase the or decrease the step size. Okay. Let us see the experimentation, how the experimentation is done using R-2R ladder network to obtain a digital to analog converter. So, what are the components required? Components required are R and 2 R's, breadboard, op amp, digital multiplier and a trainer board. Okay. Here we are taking resistors as 1.5 volts, 1.5K resistors. Okay. You can choose any resistor, 1K, 1.5K, 2.2, 3.3 or 22K, whatever you want, but don't take too much lesser values like 2 ohms, 5 ohms, 10 ohms like that, because it will draw more current towards from the source. So, to avoid more current drawing from the source, choose suitable resistor value. Okay. Next is the op amp. So, op amp is here we are using LM741. We can use any op amp, but for our experiment sake we are using LM741. Okay. So, if you can see the pin configuration here, the pin number 7 and 4 are used to apply plus VCC and minus VEE. That is the biasing voltages. Those two are the biasing voltages required for an op-amp. And 2 and 3 are the input terminals. 2 is used for inverting, used as inverting terminal, 3 is used as non-inverting terminal, and we obtain output at pin number 6. So pin number 8 is not connected to anything in the op-amp, and pin number 1 and 5 are used for offset the voltage, output voltage. And also we need a digital multimeter to measure the response of the op-amp, which will be connected at pin number 6 to measure the output voltage for the corresponding input bit sequence. Okay, these are the circuit, and this is the circuit diagram. Okay, connected on a breadboard. Here you can see 1.5 resistors are used for R and two 1.5 resistors in series for 2R. Okay, is that clear? So 1.5 resistors are connected in series to get 2R, and 1.5 resistor for R. You can choose any resistor, that's not a problem, unless it is of very low value, which may draw huge currents from the source supply. Okay, we should avoid that. Okay, this is the setup. Now we are going to apply biasing voltage from regulated power supply. Okay, we need two channel supply to apply plus VCC and minus VEE. So plus VCC is connected to pin number 7 and minus VEE is connected to pin number 4. While connecting plus VCC, what you should do, you should connect the positive terminal to pin number 7 and negative terminal to ground. Likewise, for VEE, that is negative voltage, connect the negative terminal of the power supply, other supply, to the pin number 4 and connect positive terminal to ground to get positive VCC and minus VCC. The range of voltages can vary between 5 volts to 22 volts for an op-amp, ideally. But for regular and smooth operation, we will use plus or minus 10 volts to plus or minus 22 volts. This is as per our data sheets provided by the Texas Instruments people. Okay, so the general operation will lie between 10 to 22 volts. So here we are going to use 12 volts as VCC. So 12 volts VCC should be suitably selected such that the output, the expected output should not exceed VCC. Okay, it cannot drive more than VCC. Hence, we should make sure that the supply voltage will always be greater than the expected output from pin number 6. Okay, that you should remember before applying supply voltage. So here you can see the positive terminal is connected to 7 and negative terminal is connected to ground, and in the next diagram you can see negative terminal is connected to negative terminal from other source is connected to pin number 4, and positive terminal from the other source is connected to ground. Okay, you should not confuse that. You can take a plus voltage and minus voltage from a single source. That should not be done. Okay. Next, coming to the binary inputs which should be connected to circuits. Here I am taking binary inputs from breadboard, trainer board. Okay, from trainer board to breadboard I am connecting binary inputs. So here these 4 switches are used to supply reference voltage to the binary inputs, which is of 5 volts. When it is 1, we are going to apply 5 volts. When it is 0, that is ground. Remember that the bit sequence is from B0, B1, B2, B3. That the B0, where B0 is the LSB and B3 is the MSB. Here it is. Here you can see. Okay. So this is B0 from circuit. This is B1, B2 and B3. So B0 is connected to here, B1 is connected to at this terminal, B2 is connected to this terminal, and B3 and or MSB is connected to this terminal. Clear? Let us, so these are the connections. You can see B0 is connected to B0 resistor B0, and next LSB is connected to B1, next LSB is connected to B2, and MSB is connected to B3. Clear? This is the circuit diagram, full circuit diagram with digital inputs, B0 to B3 connections to 4-bit DAC. Okay. Next, this is the full circuit setup. We are going to use a multimeter to measure the output response of the circuit. The multimeter is connected at pin number 6, which is the output of the op amp. Okay. Now let us apply. Here I am applying 12 volts for both channels. Okay, 12 volts for VCC, 12 volts for VEE. Now you can see the input is 0, 0, 0, 0, all zeros. That means all are connected to ground. Hence the output is 0. Okay. Now let us make LSB as 1. So whenever we made LSB as 1 and remaining is 0, the output is minus 0.32. Minus is because it is connected in inverting mode. Okay. So this point 0.32 volts is nothing but the step size of our DAC. We can increase this step size or decrease the step size by changing the RF value. If you want it as 6.4 volts, then you should use a 3 kilo ohm resistor, double this one. Okay. If you want to reduce this one to further value, you can reduce this RF value. Resistor values will not affect the outcome of this digital to analog converter. Only feedback resistor and the value of RF will determine the step size of our DAC. Okay. Now let us see the binary input is 0, 0, 1, 0. That is decimal equivalent of 2. Hence, you can observe here that the voltage is double the earlier one. Earlier we used to get 0.32. Now it is 0.65. Okay. So the step size will be same. So it will increase linearly. Okay. For the next value, now I am making the circuit digital sequence as 0, 0, 1, 1, which is equivalent to 3, binary 3, decimal 3. Hence, the voltage is multiplied, the bit size is multiplied by 3. Nearly we are getting 3 times the LSB value. Okay. Likewise, we can verify the output for all input combinations, that is starting from 0, 0, 0, 0 to 1, 1, 1, 1 by toggling these input, binary input switches. Okay, clear? Now the result, the tabulate the values, theoretical values from the earlier calculations and compare them with the practical values from all combinations 0, 0, 0 to 1, 1, 1. You can, as per experiment, you can do any this bit number of bits or resolution can be increased to any value, 4 bits or 5 bits, because we need only 2 resistors. For every bit combinations we need one R resistor and one 2R resistor. So here by getting those resistors you can increase the number of bits for this digital to analog converter. Okay, so these are the some points to be noted. You need to find out the value of 1 LSB from the experiment. So this 1 LSB will be the step size of your digital to analog converter. And also you should note that full scale analog output voltage of for binary code 1111, which is the highest binary value we can apply for a 4-bit DAC, will never reaches the same value as digital input. That is V reference. So even though you apply maximum value of 1111, you cannot reach input voltage, that is V reference, unless until you change the RF value. For RF equal to R, this is the condition. You will not get 5 volts or V reference when the code is 1111. So this will always be less than by a equivalent of 1 LSB, which we find out in the first point. Okay. So this case is only applicable when RF equal to R. So if you change this RF, that may not be valid. Okay, because the amplifier circuit will amplify according to RF value. Okay, this is how the experimentation will be done. Though finally we'll plot the graph for binary bit sequence versus output voltage. So you can see for 0 0 0 you will get 0 volts. For 0 0 1 you will get 1 LSB value. For 0 0 1 you will get 2 LSB values. All these are in negative direction because it is a connected in non-inverting mode. Okay. So for 3 you will get minus 3 times LSB value. Likewise, starting from 0 0 to 1 1 1 you should plot the graph. Okay, this is how the experimentation will be done. Thank you.